maybe a good place to start is the kind of dictionary learning saga. As I imagine many of you are aware, the field got super into sparse autoencoders and remained super into them for a while, and now it's a lot more controversial. I thought it would be good to maybe try to walk through roughly what happened as I see it, and how I updated over time according to what evidence, and how I recommend thinking about the broad phenomena of dictionary learning now. So, yeah, so big open problem in mech-interp is we think activations mean something, but they seem cursed, and we don't really understand how to figure out what they mean. This is bad. And it became a pretty popular hypothesis that they were in superposition after the toy models of superposition paper. And so if we think that model activations contain a bunch of concepts which are represented as directions, there's loads of them, but on any, and the crucial hypothesis is on any given input, there is not that many of them active, then it seems like we should maybe probably be able to do something like figure out which directions are active some of the time and not other bits of the time. And maybe this will magically tell us how to interpret things. And I don't know, back in like 2022, early 2023, a bunch of people were excited about this. I was kind of skeptical. It just didn't really like it would work very well. I think I was largely wrong. And there were a flurry of papers around the same time, most famously towards monosemanticity. And I think that there are quite a few things that's left out of this very simplified story that I've given of like, we think that models contain concepts that have directions, maybe, and we think that some of these light up, and we think that every input only has some of these, and therefore we think we can extract the directions. Anyone have any guesses for kind of things underspecified by that story, or different ways the world could be that would be vaguely consistent with this story? Feel free to just unmute and call out takes.
Could you repeat the exact thing that we're, like, what is the assumption here that we're operating under?
Maybe the claim is, okay, maybe I'll make a stronger, slightly strawman claim, which is going to be easier to argue against. I claim that the only thing happening in model activations is that there are linearly represented concepts, there is some finite list of such things, and on any input, there is like some finite, it's like some reasonably small number of those, say max 500, that's active, and they have associated numbers, and the activations are basically the sum of these, maybe plus a bit of noise, but the noise doesn't really matter. And that with sparse autoencoders, we can basically just recover this underlying dictionary of concepts and then see which ones are present, and sure, there'll be a bit of error, but we've basically just totally understood the thing. To be clear, I don't think anyone was actually literally claiming this at the time, but yeah, the prompt is what? Yeah. So yeah, maybe to add a little bit of extra to the prompt, we have this paper towards monosemanticity. It basically took a one-layer model that they'd trained themselves and said, we want to figure out what's going on in the MLP. Naively, we might think that we can look at neurons, but at this point, we knew that that wouldn't really work. And we have this dictionary learning technique called sparse autoencoders that seems pretty scalable. We trained it on like billions of tokens worth of activations, and we got stuff that seemed really cool. Like we have this Arabic concept, and it seems like it basically represents whether a text is about Arabic or not. The way to interpret this graph is red means Arabic, blue means not, white means and the x-axis is kind of how much the feature is activating. And there are like a couple of other examples of these. They also randomly picked some examples and showed that if you have a language model try to interpret them, or possibly also a human, they think they have a coherent pattern, say 75% of the time. And if you do it for neurons, it's more like 35% of the time. And it's not even purely correlational. We have, you can look at the kind of downstream bits of these, kind of how it directly connects to the logits, and those often seem interpretable in a way consistent with what makes it activate, in a way suggesting this is intentional. And I don't know, it's a cool paper. This is like cool evidence. Why is this not sufficient to support my strawman picture that this is a complete story?
And there are like a lot of concepts in the world, and they might not all be representable this way. And they might be...
sorry.
Oh, and and maybe they're only like combinations of these vectors, or only like have meaning later on in the neural network, instead of like in that layer in particular.
Right, but like that's fine. I would just say the model isn't representing them there. Interpretability still works if you can only see it in later layers.
Maybe one issue is some of the directions we find are just like, or some of these these dictionary features we find are just not interpretable at all. And we're like, what is this feature actually doing?
Yep, that is one issue. Well, maybe I'll break that down into several issues. We don't automatically know what these things are, because, very crucial fact about sparse autoencoders, it's an unsupervised technique. We don't tell it what concepts to find, it just finds directions and kind of works, maybe. And then what do I think? And we kind of have techniques like looking at the text that makes it activate a bunch. We also have some different pieces of information, like how it connects to the output logits, and we can use this to try to like guess what it means. And I know it's reasonably well documented that sometimes you'll be wrong, sometimes it is more subtle, but maybe this is just a skill issue, and if we get better at interpreting them, it'll be fine. And there is a different potential issue, which is that it's not interpretable at all, because we're optimizing for sparsity, we're not optimizing for interpretability. This is a proxy, not the same thing. And yeah, maybe this doesn't quite work. I know this was kind of a prior that I'd had, and then things worked way better than I expected them to, and it seemed plausible to me that sparsity was basically good enough that we could just roll with it. Honestly, I still find it kind of plausible that sparsity is basically enough, though this is definitely a controversial belief, and lots of the dictionary learning proponents think we need to be smarter than that. But yeah, as we'll kind of talk about later, they do come apart. But maybe this is fine. It turns out that activations contain some bullshit noise, and our dictionary spends like 10% of its capacity predicting the bullshit noise, and then 90% predicting all the concepts. seems kind of great. Why aren't we done? Why haven't we solved interpretability?
So I'll venture, I guess here. One is that if you're interpreting directions as concepts, do they really have a one-to-one mapping? I don't know if this is exactly how you think of some of the previous statements made, but I'll draw an analogy to something I learned in human neuroscience, where we sort of map brain activations with respect to behavior. And like in a particular behavior task, you're asking people to sort out different kinds of emotional reactions or something like that. And you will be able to map various relatively sparse, patterns in brain activation to this behavior. But then if you ask the reverse question, do those patterns only do the particular task you tested them on? That might not be true. And so certainly it seems to me if there's an analogous situation here where the same directions maybe mean different things in another context, it could be an issue.
Mm-hmm. Yep. Yeah. So that's a pretty good concern. The way I would frame it in interpretability language would be, so I think that we are in a better position than neuroscientists because we have access to the kind of full training distribution of this system, or mostly. It gets a bit more complicated if you have a system trained with reinforcement learning, because what is the training distribution? But if you've got just something trained on like internet text, you can just study this. This is a reasonable thing to do. And if it has a concept, probably that concept has got to be important somewhere. Otherwise, why would it have been learned? So you might say, all right, I'm going to try to understand what this thing means. I'm going to take 1 billion tokens of internet text, look at the 100 that all light up the most, and they are all about root vegetables. Therefore, this is a root vegetables concept. What is the problem in that chain of logic? I've looked at the full training distribution, so it probably isn't that there's some like alternative thing that was not covered in the dataset at all. Is this a root vegetables concept?
Sure, it could be a root vegetables concept. It could also be a root vegetables concept plus some other concept. There's also the challenge of like,
sorry, just to check. When you say plus, do you mean and or?
I mean, or I guess I mean could both be possible. I can see a situation where like, if maybe the top 100 are all root vegetables, there still could be like, other tokens of Letapon that are like, maybe not in the top 100, but still important and not root vegetables. But there's also like an or issue here of like, perhaps like, so you've passed in like all of your input text, assuming all of the internet text.
Mm-hmm. Yep.
Yeah, I guess I can see a case where like, you maybe are missing like, there are some root vegetables you're missing as well.
Something went wrong.
And so it's not just root it doesn't cover all root vegetables there. Maybe there's another feature that's also responsible for some root vegetables.
Mm-hmm. Yep. So the way I think about this is, so looking at the top 100 is a pretty limited cheating-y thing to do. One reason might just be, like root vegetables activated at like +10, but then cabbages activated to +9, and I think it is unreasonable to call this a root vegetable one. And so if we say try to get up something, just because I think it can be instructive. Let's see. Let's pick a mid-late layer, and let's see. I really love carrots, potatoes, and let's see. Do I get anything fun when this lights up? And maybe if I filter for the things that light up on turnips. All right. Oh yeah, warning. If you are using the Neuronpedia SAEs, at least for Gemascope, the labels are terrible. They were made by GPT-4o Mini for cost reasons. GPT-4o Mini is dumb. You should not take them at face value. So yeah, let's try looking at what these things are about. So it claims colorful and descriptive references to produce and farming. In general, if you haven't spent much time just staring at maximum activating dataset examples, I think it's worth spending at least just like an hour screwing around on Neuronpedia for intuition building. And I mean, yeah, I don't really know. Looking at this, it seems maybe vegetable-ish. It doesn't really seem root vegetable specific. Yeah. And so looking at the top is kind of unreasonable, but what if we look at randomly sampled things from different slices of the distribution? Like here, so like if this is kind of the yellow thing is like the histogram of the distribution, then we have things near the end. And if these are all about farming, and these are all about farming, and these are all about farming, maybe you can call this soft noise. In this particular case, it does seem maybe consistent. I don't know. But yeah, I think looking at intervals like this is kind of a reasonable thing to do, because if rather than just taking a max, which can always create weird pathological bullshit, you instead take the max and then random samples from kind of different chunks of the histogram, and all those random samples are farming related, then you might feel more optimistic about it. So that helps a fair bit with the or concern. If you're feeling adventurous, the even more impressive version is just give it lots of data and kind of try to classify all of them. And it turns out that when you look at lots of data, rather than just a few randomly sampled bits from earlier in the distribution, you often discover that your label was limited. Anyone have any guesses for how? Or like what the discovery is?
Quick question. For that feature we just looked at, do you have intuition for why the negative logit is like the negative logits are so high on like whiskey or like other tokens? Like, what is the like? I guess
question. No idea.
Logits is being like, yeah, related to a concept. Like, what is the opposite of the concept? Is it just something arbitrary we don't fully understand?
I mean, I don't know. I don't have confident takes about this one specifically. I do think that, actually, I'm kind of curious what happens if I regenerate a label for this. Oh, I need to log in, whatever. So yeah, so one thing to note here is I think at first glance, you might think, oh, it says whiskey everywhere. What's up with this? But you would expect that all of these unembeddings are like highly similar to each other.
Yeah.
Because the whiskey concept might tokenize differently depending on the exact like grammatical context you're in. And so the kind of initial reflexive reaction you might have of like, there's 5 things to do with whiskey, it has to be about whiskey, might be kind of a
yeah.
Why it's there? No fucking clue. I think sometimes it will just be kind of random, sometimes less so. I'm sure there are like statistical tests you can do for is it kind of anomalously far out? Like, but I don't off the top of my head wants to claim knowledge of whether minus 0.76 is unusually far out, such that this suggests there's something special rather than just what you would get if you have a like Gaussian distribution over like 200,000 data points and you're taking them like bottom 10. In this case, right tag helper is a kind of cursed token, and it wouldn't surprise me if it's a glitch token a la solid gold Magikarp. That's just in the tokenizer for stupid reasons, and the model never really uses it. And so it kind of wants to cast the logit to a very negative value. And so that incentivizes it to have a big unembedding that will point in a negative direction. Common confusion is that because these models have tied embeddings and unembeddings, this means that the embedding of right tag helper is the same as its unembedding, which means that that's also going to be big, and it just doesn't matter because this will never arise. Possibly this actually does occur a bunch in code, I don't know, so this might be completely off base. But yeah, so the place I was going, unless anyone else wants to try to answer the question of what goes wrong when you systematically study, say, 1 million data points rather than just sampling.
I mean, I would imagine that one of the things that you wouldn't want to happen is just it lights up a little bit for a bunch of them, and then you don't know what to do at that point because it's, yeah, we can't isolate it to something specific.
So, but in that case, you would just say, it seems to light up for like 5 totally unrelated things. I don't know. Doesn't seem interpretable. The trap is if you think it's interpretable and it isn't. So the core problem is that if even just this entire histogram is apparently only like 0.226% of all data points, or like all tokens, which means that there's, you know, like almost all of it is not even on this histogram, let alone in the region that we care about sampling from. So what happens if there's just tons of stuff about farming in that 0? We wouldn't notice, because we're systematically filtering the data we analyze to be things where it activates. And so this means that it's very easy to have a hypothesis that is like way too general, and it might be the case that this is some like cursed, warped version of this. Like maybe it's colorful references to produce and farming, but written in the specific style of certain farming magazine outlets or something. It's probably not that one, but like, or maybe it's that excluding kind of that, but excluding a bunch of specific special cases of this that have their own dedicated latents. And yeah, I'll say more on that in a bit, but maybe that just to speed run through the history of dictionary learning is, yeah, like this paper and others, like one from Poogie Cunningham made like a pretty big splash, seemed super exciting. It was like, oh my God, we just found a thing that makes activations interpretable. This would be such a big deal. This is so good. And my team kind of pivoted to focusing on SAEs loosely on the grounds of, well, this seems like it's plausibly an extremely big deal. We should probably check. And I think that there were then some like not great dynamics in the community around this. I think first off, just a lot of people piling into one research direction is often kind of suboptimal because people step on each other's toes and there's diminishing returns, and this means other areas get neglected. And I think that happened too much here. And I think the other thing that went wrong is I think that people kind of anchored too much on the early work that had happened here. So e.g. that sparse autoencoders were like basically the right way of going about this, when really all that had been shown was dictionary learning is a sensible thing to do, and SAEs happen to be an effective method of doing this. though there was also some messiness where Anthropic were like, yeah, we kind of looked into a bunch of methods, SAEs work the best. We haven't really written up the other stuff we did, but like, and this kind of also baked in assumptions like the activations were the right thing to study. Kind of later on, you have things like Lee Sharkey's sparse parameter decomposition, saying maybe weights are the right thing to study, etc. And one thing that kind of happened a bunch was people working on just kind of hill climbing on SAE-related things. I mean, my team was also somewhat guilty about this because we came across some better SAE architectures like gated SAEs and jump Trello SAEs, and we're like, we should share these. But I think the one thing you could reasonably criticize about this line work, including ours, is that the main metrics we used were basically what I think of as approximation error. Like if you substitute in the output of the sparse autoencoder and then run the model, how does loss change? Kind of how does performance go down? There were also some specific cursed things about this metric where the baseline that was originally used was zero ablation to the output of the SAE, and looking at how much of that made things worse and then dividing by this. Can anyone see why this explains why everything in the left-hand graph is above 0.9?
Sorry, I didn't understand what you meant. So like the zero ablation or what?
So concretely, what this graph is showing is you take the output of the sparse autoencoder, you replace the activation with this reconstructed activation, you finish running the model, you look at the kind of how much worse next token prediction loss gets. You then do the same thing, but rather than substituting in the reconstruction, you substitute in just zeros for that activation. And then you look at how much that makes loss worse. And then you take the ratio, and that's loss recovered.
I'm still confused. Like, why would it make any sense to substitute in zeros? Maybe I'm misunderstanding the like.
No, it's just a terrible idea. But I mean, the intuition is like, how much better are you than some dumb baseline? Because that's some intuition of like how good your thing is. But zeros, oh, I know, Alex, if you were going to answer this.
I was just going to say, could it be that basically that layer doesn't really matter? And so that when you do like the ratio, it looks favorably because what you've kind of ablated out doesn't change the loss much to begin with?
So that wouldn't be that big a deal because if it didn't really matter, and it didn't really matter to the same amount when you did the reconstruction, then you actually would be getting like zero. Because like the point of the divide by what happens when you do a dumb thing is to kind of baseline what is a reasonable amount of loss. And basically the problem is with residual streams specifically, the residual stream is like the entirety of the model so far. It is the bottleneck connecting the first and second halves of the model. If you replace it with zeros, everything goes completely haywire, and so your numbers just get significantly inflated. And you can improve it a bit with like mean ablations, and it's like somewhat less bad for kind of specific layers, but zooming out a bit from specific critiques of exactly putting zeros into the residual stream, I think that one of the main problems with metrics like this is I just have no fucking clue what they mean. Like, this is about 95%, and it's only using like, wait, maybe it's only using like 10 latents. Is this good? Is this bad? I don't really know. I mean, you can look at the direct amount that loss decreases, and that kind of also tells you something, but it's kind of messy, and one of the problems is that, like, if this was kind of at 1, or like 1 minus epsilon, then I might be kind of comfortable saying, yeah, I'm pretty sure that the stuff my SE is not capturing doesn't really matter, life is good, I can move on. But, like, what does 5% mean? And in fact, here, 5% actually should mean much more than that. It's just that we're dividing by a really big number. This is 1 minus the kind of ratios. So if the denominator is really big, that means it's very close to 1. Sorry, I should have flagged that earlier. And yeah, this is kind of unsatisfying. I personally would guess that gated SAEs were an improvement, and I think there are like some various conceptual arguments that I kind of buy for this. We also checked things like, are they still interpretable? But I think that not having great metrics for is this thing actually getting better was one of the many issues. And I think that another, and this is kind of downstream of not having clear clarity on like why we were doing this or like what these were for. Because I think there are 2 very different reasons you might like SAEs. Reason 1 is you're like, I'm gonna completely reverse engineer this thing. I'm gonna understand like as fully as possible what these activations mean. There is some ground truth here. I'm just going to like push as hard as I can. Maybe there's some things that don't quite fit into the paradigm. Maybe there's some obscure nonlinear things, but whatever, it's okay. And that's one way you might think about it. Another way you might think about it is I'm never going to fully understand this. Regardless of whether there is some clean ground truth or not, my methods are flawed and they are never going to not be flawed. But they can be useful. And I want a tool that will help me interpret models, and it doesn't, you know, it could have a loss recovered of like 70%, but still be a really useful tool that gives me true insights about the model. It's just only capturing a chunk of what's going on rather than the whole picture. And if what you want to do is make claims like, yeah, I feel pretty good about what this thing's telling me, or like, yeah, it seems like maybe the important things going on here are probably X, Y, and Z, and like here is some causal evidence of this, that's good. But then on the other hand, if what you want to say is like, I'm really confident there is no hint of deception here, this model is amazing, it's totally clean, I think that this just isn't really the kind of tool that's going to get you that. And even if it was, what is the level of loss recovered where it could get you this is just kind of really unclear to me. Can anyone think of reasons why, if I have a model that I claim could be deceptive, if I claim I have a model that could be deceptive, and I look at it with an SAE, it's like a pretty good SAE. I've tried pretty hard to train it well. It's got a loss recovered of like 96% and like 200 concepts lighting up per data point. And I search through them and I'm like, yeah, there's like not really anything here that's about deception. Therefore, the model is not deceptive and we're fine. And we can release it into the world. What are ways the chain of reasoning could be wrong?
Could it be that not everything is a plain linear direction?
Yep, I think that I'd maybe phrase this more generally as there are almost certainly things not captured by the sparse autoencoder. We know this is the case because when you make it bigger, it gets better. And I don't think people have yet found a size where it doesn't stop getting better for reasons that are for reasons other than your training is no longer stable because it's a harder problem to train big things. One possible reason you might not find things is that they are like fundamentally not linear. There might also just be like other reasons. It might not have had capacity. It might have just been weird random noise in training. Like fundamentally, this is a neural network that we are training to interpret another neural network. Neural networks are not clean deterministic tools. I still maintain that we have basically no evidence of genuinely nonlinear features in language models, but it is entirely possible they exist. They're just way harder to find. Any others?
I guess like deception could be like a corner case of behavior. But if you look at like most of the model behavior, it won't capture that.
Yeah, that's a good one. But what if the model does something sketchy and you're trying to audit it and you're like, I don't see any deception neurons? All right, so maybe the final thing I'm trying to get at is you could have just incorrectly interpreted your features. You could, I don't know, totally plausible that something that is deception related does not obviously look deception related. It totally could. I mean, models definitely know what deception is. They're trained on tons of books and movies with deceptive characters. You know, they're trained on 4chan, all kinds of crap. And so, yeah, this might give you, it might work, but it might not. All right, so I've gone pretty deep into this tangent, maybe just recapping the key points from this and zooming a bit back out. A bunch of people, myself included, were excited about things like hill climbing on this technique. I think the community made various mistakes around like lack of diversification, kind of taking the initial work as too much of a given and not like questioning the assumptions or exploring enough. Another big one that I may touch on in a bit is not like red teaming the technique to see if it's actually doing what we think it's doing. And the final one is just like not really having good metrics and it not really being clear how to interpret the metrics we had. Where like you might hope that, you know, if a thing recovers the loss better, it's probably better for the things we actually care about, but this is like a pretty loose proxy. All right, so I have gone pretty deep into dictionary learning. I think there are two options for where this could go from here. I could basically spend the rest of this talking about dictionary learning, lessons taken from this, what I think the interesting takeaways are, how I recommend thinking about it today, and then probably tomorrow do more of the, what do I think are the important directions now, what's happening, what's alive in the field, or I could try to like aggressively speedrun dictionary learning and try to do some of that today. Can people put in the chat dictionary learning, continue for just continue on this, and speedrun for wrap this up ASAP and move on. Hey, continue it is. I am boring people less than I thought. So maybe let's return to the notes and kind of draw out some of these threads. I think they're worth digging into more. It's like initial hype, and yeah, I maybe want to underscore that I still kind of endorse my initial hype, attempting to look past hindsight bias. I think that this worked way better than I expected it to. It really wasn't obvious at the time how far this technique would go. I think I probably should have been like more careful, but I think that it still is something of a big deal and could have been like a really big deal, and people investigating it to figure this out was worthwhile. And I still think SAEs are like a useful tool that I will sometimes recommend as the correct things to use in the project. But yeah, all right, so initial hype, problems, yeah, lack of diversification, lack of red teaming, or metrics, not clear what the goal is. And yeah, I think that one of the kind of initial concerns about SAEs was this is like on a tiny toy model. Is it really going to work on real models? Is it just going to like break? Or the concept's going to be too abstract or too myriad? And yeah, it turns out it actually just works fine. I think that this was like reasonably clear after this paper where we got it working on like a, at the time, modern 7B model, Gemma 1. OpenAI had a paper doing it on GPT-4. Anthropic had their famous Golden Gate Claude paper doing it on Claude 3 Sonnet. And yeah, there were kind of, I would, yeah, roughly summarize the state of the evidence at this point of, say, mid-2024-ish as kind of, there are a bunch of cool things we can do with these. Like, I think that, you know, it found some like genuinely pretty abstract concepts. It initially seemed like maybe it was just responding to the input text, but say in Claude, they found like a sycophancy concept. Oh yeah, I should maybe say terminology-wise, a unit of an SAE was originally termed, or well, not originally, it was termed feature by Anthropic's Polysemanticity paper. I think this is an incredibly confusing word, and I try to use alternatives like latent, except when I forget. The reason I think it is confusing is feature is simultaneously used for a unit and for the concept that a unit potentially, but does not necessarily correspond to. And I think that when you have, let's see, I think there might have been a sentence in here. I know, too many examples of features. Yeah, you will sometimes get extremely confusing sentences, like, the Donald Trump feature is about the Donald Trump feature, or something. And I think this is terrible, and I refuse to use words this confused. Though I think the community has not quite settled on what we think the least terrible name is, because people also critique latent. But all right, rant aside, this is a pretty cool concept. It seems actually kind of abstract and like sycophancy, and I think that basically, yeah, SAEs seems like they could have stopped working at multiple points and they kept working. But maybe returning to the kind of problems I was trying to highlight, I think that, yeah, maybe let's zoom in on kind of what is the goal here. So I think there are a few, kind of, as I was saying, there's the kind of meta goal of reverse engineer as much as you possibly can. Personally, I don't actually think this is really a goal of many people in the field. Oh, that's not quite true. I think that people from the safety community who talk about that kind of stuff largely mean it as a means to an end, and they just think that if we can like reverse engineer the thing as much as possible, we'll be way safer. But this is a proxy, and when you have a proxy, you want to be clear to yourself about what actually is happening, and like what the proxy is representing and not representing. And then there's much more pragmatic things, like are there tasks we could do more easily? Like if we, you know, maybe we want to make probes that will detect like users with harmful intent, but users are going to have loads of jailbreaks, and it's going to generalize badly out of distribution. And so let's, yeah. So, you know, we want something that's kind of interpretable, and it's trying to get the heart of the like true concept. So a thing I believed was that SAEs, or at least sufficiently good SAEs, should make it possible to train probes that generalize way better out of distribution if you instead make the probes like a sparse combination of SAE latents. And in our blog post entitled Negative Results and Deprioritization of SAEs, which, you can maybe guess the results. We tried this, and linear probes just completely crushed SAEs. And so I would consider, can I do this specific useful thing with the technique? An example of a downstream task, a kind of objective metric where if you are doing well at interpretability, you should be learning. Or learning is not quite the right word. If you're doing well at interpretability, you ought to be able to do better on these tasks. They might not be your ultimate goal, but they're like a way of tracking progress. And if you are making progress, you really should be making progress on these things too. And they're objective and measurable. And I kind of know how to interpret the results of these somewhat better. Like, is it better or worse than a linear probe? If yes, it's doing something real. If not, maybe it's doing something real, maybe not. I don't know. I have sometimes heard people say things like, great SAEs have never been tried, and we just need to like find better methods, but yeah. And I think that, there were like a couple of other examples at the time. One of my favorites is one of my maths projects on kind of just trying to do sparse probing on a bunch of things that we thought SAEs would work better on. Like, what if you don't have much data? Surely the inductive bias of being interpretable should help. Or what if you have like loads of biases in your data or tons of noise? And yeah, logistic regression wins. We even tried this kind of quiver of arrows approach where we were like, all right, let's take a bunch of techniques and then let's do them all on a validation set. And then let's take the best ones on the validation set and then apply that to the test set. And let's do this with and without the SAE arrow in our quiver. And if SAEs add anything, they should probably make us better, even if, most of the time we'll be using other techniques. And that also didn't work. And my personal takeaway from this is something like, SAEs are not precise. They were never trained to find specific concepts we want, like harmful intent. We can make it easier for them. Like, one of the things we did in here, I believe, was mixing in chat data, and found that this made it better at the task. It made it more salient to track things like user having bad intent, but it wasn't enough. It closed like half the gap. And my rough conclusion is linear representations are OP, and models just genuinely do have fairly interpretable linear representations. SAEs can find approximations to this with issues that I'll get to in a bit, but they aren't optimizing for finding that thing. They are kind of vaguely optimizing for something roughly like that. And they will be worse than a thing that is more directly optimizing for what we want. And if it's a concept where we kind of know what we're looking for and we can make data, we can use supervised techniques. And so in general, if you can use a supervised technique, I think the SAE is unlikely to win. Not like out of the question, but not great. So that's kind of supervised stuff. But as proponents of SAEs could reasonably defend it as, but actually SAEs should kind of help us discover things we didn't already know, things we weren't sure would be there, kind of challenging our preconceptions. And I think that this is a really important point. I think that it's very easy in interpretability to kind of impose your guesses for what's going on onto the system. Supervised techniques are like an extreme case of this. Your supervised technique might just totally fail, which would tell you maybe you're missing something, but maybe it looks like it works, but actually there's like a bunch that isn't there. And I think there's like a handful of like pretty fun case studies here, two particularly close to my heart. One is my like kind of modular addition grokking work, where I totally did not expect there to be weird-ass Fourier transforms in there, even if in hindsight it kind of makes sense that if you're made of matrices and you're trying to do modular addition, representation theory and trig and rotations are like the right thing. But like, this was pretty non-obvious, and I think it was pretty good that I was just messing around inside the model, not with like a kind of formal technique, but just kind of looking at data, making guesses, looking for patterns. I did use things like PCA that helped kind of find some structure in the noise. Another kind of famous case study is there was this paper called on Othello from Kenneth Lee, where it's like probably a really cool paper. And what they did is they kind of, so Othello is like, for those unaware, Othello is like this game that's kind of made like a much easier version of Go, and they trained a model to play it, and kind of predicting the next token, and then they trained probes on it and discovered that despite only ever kind of being told the next move in kind of chess notation style, it had learned to simulate the Othello board internally, and they could kind of probe this even better. They could kind of optimize the activations against their probes to kind of think there was a different board state, and it would now make moves consistent with the new one that would have been illegal in the old one. And this is like a pretty excellent paper. But the weird anomaly was that using linear probes did not work. Using nonlinear MLP probes worked. And yeah, when kind of probing for like, basically kind of training a probe that just outputted a bunch of different logits for like, is cell A1, black, white, or blank, etc. Kind of how well did these do? And I did some follow-up work where it turned out that actually it was more complicated than that. Anyone who doesn't know the answer want to try to give a guess? What was missing from this analysis? Well, to maybe make it concrete, I claim that there is no linear representation of the Othello board in this model because I probed for it, didn't work. But I did a nonlinear probe and it worked, and I could edit by optimizing against this nonlinear probe. Therefore, it is like, in fact, really there and really causal. Therefore, I have found a nonlinear representation to straw man. Also, out of curiosity, raise your hand if you do know the answer to this. Wild. Mech-interp fashion moves on so much. I assumed this is boring history. All right. Anyone want to hazard a guess? Maybe raise your hand if you have a hypothesis. All right, Elle, what's your hypothesis?
I guess there could be some equivalent representation of the board state that you can probe for linearly. And so like, I mean, I guess that's sort of cheating in that like, hey, the equivalent representation is you pass it through some MLP that you learn. But like, maybe there's some like, I don't know, more combinatorial thing of like, but I can't think of one off the top of my head other than like stuff about, okay, is this row, how many things are in this row, or things of that nature? Or is this
right. You are correct that there is a linear representation that is an alternative representation of the board, but it's not about like rows and columns. It's still kind of each cell one at a time. Any other guesses? Feel free to just call out.
I mean, I could start imagining statistics about cells, about like what's the distance to the nearest like black one, or what's the legal moves that you can play in this cell, or Is this
Much
a-
simpler than that. Okay, I'll give people a hint. This model is playing both black and white.
Is it something about which player's turn it is, or
Mhm. Yep, warmer.
And to be clear, the original representation is like, is there a black or white chip in this cell or nothing?
Yes. Kind of, yeah, like train a 3-class probe and see basically what you find.
Like,
And go ahead.
like the alternate representations would be like the same player would be playing, and they could be much more linear.
But like, what is the alternative representation?
No, I mean the alternate state. So first move is played by player 1, and then player 2 is playing the second move. So you leave that player 2's move and only look at player 1's move, and those 1, 3, 5 step 1, 3, 5, and those are linearly representable. Versus 2, 4, 6, 8 are separately linearly representable.
Gotcha. So basically, you'd train like a set of linear probes on odd moves and a separate set on even moves.
Yeah.
Yep, basically correct. So roughly, let's see. Yeah, so I think over here may have been, yes. Yeah, so basically, it turns out that what's going on is that if you're playing both black and white, it's like fucking useless to represent this cell as black, because that means completely different things on odd and even moves. But if you represent this cell has the current player's color or the opposing player's color, now that's perfectly consistent and you can reuse all of your circuitry. So basically, yeah, like I was kind of staring at things like neuron max activating dataset examples and stuff like that, and found that there were some neurons that kind of seems to roughly activate on, let me see if I can find the neuron. So yeah, basically, okay, I can't find a picture. Oh yeah, here's a fun one. So I'd found this neuron that was important, and you can look via like just activation patching on some random hand-coded things I hacked together. And this is a heat map on just like 50 random games of where it activates. The x-axis is move, and it alternates. This is a really big hint that something roughly like, something roughly like the different things for odd and even hypothesis is happening. I then just trained some probes, because YOLO, on odd and even turns separately, and it totally worked. And then later discovered it was even simpler, and you could train a probe, one set of probes that would just kind of negate itself every turn to kind of swap between mine and theirs. And that was a very fun project. For anyone curious, I have a series of blog posts on it that we later turned into a paper, and I think people might particularly enjoy this one, which is roughly a kind of research log of the process of my random weekend hackathon where I found this. And why I made random weird decisions at different points. Yeah, if you just search like Neil Nanda Othello alignment forum, you should find it pretty easily. And yeah. All right, zooming out of that tangent because I like that paper. Yeah, it seemed, I think this is both interesting as a case study in sometimes the right representation feels really natural in hindsight, but like you didn't think of it. And therefore, an interpretability tool that can surface unexpected things to you is great. And if your interpretability tool can't, this might be very limited. Notably, I think interpretability is also one of the few areas of ML that can do this at all. And secondly, I think that this is actually some pretty great evidence for the linear representation hypothesis, because I think there was actually a pretty good case that they had found a real nonlinear representation. The evidence seems to point in that direction. I had faith, and my faith made correct predictions about reality. And yeah, I think that surviving falsification just is one of the few ways you can get evidence for a extremely hard to prove hypothesis like this. And all right, so basically, I think that having methods that work in unsupervised ways is a big deal. Are SAEs good for this? I think the answer is basically just clearly yes. Partially, it's just really nice to be able to, say, write some text and then just read through guesses for the concepts that are represented here. A more user-friendly version of this might be this beautiful demo that Neuronpedia made for our open source SAEs. It's very cutesy, and yeah, this is great. This is just not a thing we could do. And you need to kind of red team this, and it might be missing things, it might be misleading, but it can totally surface things. And I personally think it's very plausible that some of the first kind of scary deceptive language models, if you run an SAE, there will just very obviously be a big latent that also lights up on things like deceptive characters in fiction. Because, you know, if something's obvious, it's probably captured by the SAE. And one of my, yeah, I think there's like quite a few nice case studies of this. Maybe kind of running through them. I had a really lovely maths paper from Oscar Obeso and Javier Ferrando called, like, Do I Know This Entity? On how if you, it basically seems like models have an internal representation of, is this an entity I kind of recognize or like have seen in training or not? You know, you can change yellow submarine to turquoise, and now the what the fuck is going on latent lights up, and the I know this thing stops lighting up on submarine if it's turquoise submarine rather than yellow submarine. My personal guess is that just as a side effect of factual recall machinery, the model outputs an additional kind of tag saying, I remembered something. And do I recognize this is very similar to do I know facts about this? So we might just be telling that. We actually categorized things by, like, if you ask the model factual questions, does it get most of them right about some entity? And you know, credits to Oscar and Javier. They basically discovered these in the research sprint. Great sprint. Interesting original discovery about models. And yeah, I think that kind of now I know this exists, it really wouldn't be very hard to, yeah, it really wouldn't be very difficult to make my own data set and make a steering vector by taking the mean difference in activations or training a probe. The important thing is, like, having the idea to do that in the first place. And there's like a bunch of other kind of qualitative examples, especially in Anthropic's papers. I think Anthropic does a very good job of just having lots of rich qualitative case studies. Let me see, was there something surprising in this paper? Oh, yes, I think there was something about, they kind of looked at the assistants. I think they might have looked at concepts that light up on the assistance token in kind of like chat formatting. And this often seems to represent, it maybe seems like it kind of represents things about the model's conception of itself, or like what it thinks is going on, because models often use kind of dumb tokens like full stops or template tokens like this to kind of store summarized info. And I don't know, it's an interesting list. We've got kind of it knows it's an AI. It maybe doesn't consider itself to kind of have a body. Existential threats, that's a fun one. Gotta love models thinking about that when you talk to them all the time. Being trapped. Remembering to say that it doesn't have consciousness, because that's a extremely crucial part of the model specification. Something that vaguely feels analogous to being an assistant, breaking the fourth wall. I have no fucking clue what any of these things mean, but I think there's probably something going on here that could be uncovered with further investigation. And I think that anecdotally, it sounds like people in Anthropic have found a fair amount of interesting things by looking at assistant tokens, and often think this is a fruitful place to look. Harriet?
It's slightly a tangent, but with Golden Gate Claude, did they basically make sure that all of basically the Golden Gate feature was alive like this for any given input prompt, and they just amped it up? So if you looked inside the model when you were talking to it, you would just see the Golden Gate feature over and over.
I didn't quite understand the question. What they did was they took the Golden Gate Bridge. Actually, raise your hand if you know what Golden Gate Claude is. All right, it's about half the people, so totally worth explaining. Basically, I believe some random person at Anthropic, after this came out, I think they worked with product or deployment or something, was this is really cool. And in this paper, they kind of also were showing that these had causal effects. You could kind of make the model always think about it way more than it normally would on every token, and then see what would happen. And one of the things they had a case study for was the Golden Gate Bridge. Oh yeah, another fun thing found in this paper and others is that this is a multimodal feature. It lights up on pictures of the Golden Gate Bridge as well as text. About how gorgeous and glorious it is. And yeah, so they've released a demo called Golden Gate Claude, where just anyone could talk to Claude obsessed with the Golden Gate Bridge. And it was beautiful, and it went ludicrously viral. And I think probably just substantially increased the amount of interest in mechanistic permanently or something. It was really weird. I do not think people should have been as excited about it as they were. But all right, here are some screenshots. It feels like there's no joy anymore. Joseph B. Strauss started planning the iconic Golden Gate Bridge. He faced a challenge not unlike yours, but the Golden Gate Bridge was created. Let's make 20 questions. Yep. It was weird. Beautiful proofs about the Golden Gate Bridge. And it was somewhat deranged, but interesting. All right, maybe to take some of the questions. Sorry, I missed Dennis's question ages ago. I'll probably talk about that later when I'm talking about SAE alternatives. Let's see. Lewis asks, do they explore how the entity stuff related to hallucination? Yeah. So these directions of do I know this entity or not, do mediate whether the model will hallucinate or not. or like whether it will refuse to answer or not, which is different. It's kind of the absence of hallucination, not the inducement of hallucination. The way I think about it, models want to say plausible things. This is a really strong bias induced by pre-training, and post-training just kind of installs an overriding reflex of like, refuse if you don't know. But this is kind of janky and messy. And there's also some dumb things where like most benchmarks are just reward random guessing a lot more than they reward saying I don't know, which is stupid, but whatever. And yeah, so it like causally mediates this, but like this isn't an explanation in my opinion. It's more like a symptom. It's like this is one of the downstream causal nodes in the should I refuse to answer or not circuit, which I personally think is more important than the hallucination circuits, because we want to kind of debug that circuit. But yeah, like why is unclear. But we largely kind of found that it was causally relevant and then didn't really explore this further. I think they actually spent like a really long time trying to do that and didn't make that much headway. And then we decided to just YOLO their sprint project and a bit more into an iClear paper, and then it got an oral. It was really weird. But it's a good paper. I like it. So yeah, a sequel paper they did was saying kind of, can we detect hallucinations using this? And did this hallucination probes paper that went viral on Twitter recently that people might have seen or been playing around with. Basically, I'd say that the papers are kind of spiritually related, but like technically not actually very related. These are linear probes, and these were trained with a data set they made. The way they made the data set was by saying, okay, so we want to probe for hallucinations. Most hallucination detection is kind of useless in the real world because it's about question answering. It's just like, is the entire answer true or not? But like, this is not actually realistically how people use models. And you know, if it's initially basically correct, but like a bit's off, and then as you go on, it becomes more and more cursed. You don't want to just like not show the user the thing or tell them this is not fully correct. So you kind of want something you can do per token in like a streaming way, and probes are good at this. They're like very cheap. You can run them on every token. Life is good. And essentially, let's see how to phrase this. Essentially, they made a synthetic data set by getting a bunch of model generations and then having Claude with web search spend an extremely long time and a great deal of API credits, making a really high effort data set. It took ages. And they then, you know, got results like this. Data, it makes a difference. Yeah, I think the generally common wisdom among competent ML people is putting time into making your data good has enormous returns. Yeah. Oh, actually, I noticed we have Javier on this call. I don't actually know if he's currently at his computer, but feel free to jump in with takes.
Well, yeah, I'm actually here.
How accurate is my rendition of the story?
Yeah, exactly. I think it's like that. I think the key was the data set. And I think we were lucky because we tried different things, but the fact that Claude, well, these LLMs with web search included, they were released. That is what allowed us to actually build a good data set. And with a good data set, then you can train a good probe. But yeah, it was the key.
Yeah. So yeah, I think my interpretation of this is that they're not actually hallucination probes, they're factuality probes, like truth probes. As I think we basically claim in the paper, because the data sets transfer between models, and if they're hallucinations, that'd be kind of odd because you wouldn't really expect model hallucinations to transfer. But especially given that you're kind of probing after the thing has been said, you're kind of not actually looking at the model's machinery by which it generates this token. You're looking at its machinery analyzing the token it just generated. And it's almost certainly got a representation of like, was this true or not? Which will overlap substantially with like, was this hallucinated or not? If the model kind of knows that at the very least, it can't verify what was said. It should have a representation of like that, even if it doesn't know the right answer. And yeah, didn't you have some result that like the Llama 70B dataset was better than the dataset generated by some of the smaller models on those models or something?
Sorry, what about the Llama 70B? Like it was better.
Am I correct in thinking
detecting hallucinations?
Yeah,
like those
am I
were better there. Yeah.
Am I correct in thinking that the dataset generated from Llama 70B completions trained better probes on some smaller models than datasets from those smaller models?
They were similar, but we found those cases, yeah. But in general, it generalized pretty well across models. That was a bit surprising. But as you said, this is more of a fact-checking thing, where once you output the token, then the model kind of checks, or the probe detects this, that the model is actually checking whether the output is correct or not. But we are not predicting whether in the next tokens it's going to hallucinate.
Yep.
But,
and yeah, no, I thought this was a really cool paper. Great work. And I think that it's kind of interesting as a case study in being kind of inspired by exploratory interp discovery, but not actually really using the details. Just, specifically the way they made the data set was kind of taking entities, having Claude extract entities and then using web search to say, was this entity correct? Because that's a lot easier to do in a streaming way than like, is this sentence or clause correct? Which is like much weirder and fuzzier. And I don't know, to my knowledge, there was just not that much work on token level hallucination detection. And you kind of had to invent some of, or like kind of adapt baselines from short hallucination contexts to long ones. Though there's also did confusingly well on short ones. I think one of my favorite results was that it generalizes to incorrect maths working, where I think, were these examples cherry picked from like about 10 runs on mathsy things for the best looking things?
yeah, something like 10 examples.
Yeah. So, you know, more impressive than it should be, but not that much more impressive than it should. A regular reminder, always ask the question, how cherry-picked was this when seeing impressive demos that are qualitative and clearly selected by researchers? But yeah, it's just like, it's doing some simple maths, finding a geometric series, and then I think all of the working is correct up till here. And it starts flagging these as hallucinations, and it was never trained on maths. And I know some people are currently doing mini projects on like, does this work as a lie detector? And I'm very curious about such questions. If the model just actually has some like clean, persistent representation of truth that a sufficiently good data set has kind of tapped into, that seems pretty awesome. But yeah. All right. Zooming back out, I think that one of the exciting developments more recently, kind of like in the last year-ish, has been what I think of as downstream tasks for understanding or for unsupervised discovery, like objectively measurable things that you should succeed on if you, objectively measurable tasks that you kind of should succeed on if you kind of have a good interpretability tool like an SAE, and where if you don't, you should do less well. Yeah, maybe I'll give people a moment to think, and they think of examples of good downstream tasks that test understanding, where this is kind of a big deal because ultimately that's what I want to do with interpretability. I don't really care about whether I can classify user intent better. Like that's nice, but it's not really why I'm doing this work. But things like just really understanding what's happening in this model, what is its motivations, things like that. Anyone have any ideas?
I guess like reward hacking type of situations.
But what would the metric be?
Well, I guess I'm imagining like the thing motivating the model could either be like, oh, I want to get more points to make these unit tests pass, or I want to like help the user write quality code or something like this. And then the metric could be like, is it passing hidden unit tests or something? And yeah. Wait, are you asking a metric about something else?
I'm kind of asking for a metric that tells you, yes, you have a great tool for unsupervised discovery. I think in that case, you could probably just make your own data set and train a probe and do basically fine.
Right.
And all right, so Aditya put in the chat, 2 models are doing the same thing, one for the right reasons, one for the wrong reasons. Yep, I like this one. I think that the key ingredient you need to make this work is this idea of model organisms, of kind of designing models with properties we have chosen so we can then investigate. Like a simple version of this would be you fine-tune a model to always do the thing that would kind of screw over the user when it thinks it can get away with it. And you have another model that's just like a bit confused, and you find some example and you kind of find some settings where the 2 models do basically the same thing. This one's kind of difficult because I feel like you could probably solve it by just writing your own examples and seeing what the 2 things do. But I think there are ways you can make something like this work. So one example of a downstream task here is hypothesis generation about a data set. So there was this lovely paper called like SAEs or something. No, I wanted. Nope. All right. This one, yes. Well, search engine optimized. Where the premise of this paper was like, we're doing data science. We are just going to take some data sets that have labels, e.g. newspaper headlines labeled according to who clicks on them, and then see if we can come up with properties of headlines that are more likely to be clicked on, e.g. about politics, or has exclamation marks in it, or something like this. And there were LLM-based baselines for this, and this apparently is like a task people had studied. And what the people in this paper did is they used SAEs to do this by essentially looking at which latents, by like using a kind of text embedding model to convert each headline to a vector, creating an SAE on those embedding vectors, looking at the latents that lit up a bunch, looking at the text that made those latents light up in general, saying this is a hypothesis. And you're going to get a lot of false positives here, like, you know, you labeled your latents badly, or it's kind of spurious. But what you can then do is use a language model to label your trained set of headlines with, does it have this property or not, with no reference to the SAE, and then say, is this useful for predicting whether someone clicks on it or not? And like half of them will work, half will do badly. And in this paper, they found that like SAEs were just a pretty solid method. And they generated kind of more hypotheses. They kind of often had bigger effect sizes. And generally, I don't know, more green things. And I think that, well, like, yeah, this is the SAE-based one. These are the kind of baselines. And I don't know, I really like this paper. I think it was just a simple, well-scoped thing that actually kind of tracks the thing we care about of, can you generate useful hypotheses about a data set? That was also just really easy to actually measure. And I don't know, some of you might have seen the data-centric SAEs paper from Nick and Lily, some of my 8.0 scholars in the last cohort, where they basically were like, SAEs for data analysis. It just seems like there should be a load of things you can do to understand data better. And their idea was basically to build what you can kind of think of as like an SAE embedding vector for a document, where you take the SAE activations on each token, you then take the max across all tokens. So you're kind of saying, like, which concepts are in this document at least once. And now you have the vector, but also each element in the vector is hopefully somewhat interpretable. And so you can do kind of the things you do with normal embedding vectors, like clustering them and retrieval. And you get interestingly different results. E.g., it's often kind of difficult to do retrieval. That is, I have a query, find me the data that is like this query, using standard embedding models, because actually, yeah, can anyone see why standard embedding models struggle with model in repetitive loop, where an embedding model, for people not aware, is just like a model that takes some text of arbitrarily many tokens and converts it to a single vector that's kind of trying to contain the semantic info of that text.
Well, this paper took like the max, right? So, like,
leaving aside what this paper did,
but
why
well, I
would
guess,
normal
like,
things fail?
but like, if I had a very long chunk of text, right, like different parts of it might be about different things, and I guess the embedding could add those, and maybe the addition, like, I mean, I guess if they're like sufficiently orthogonal, maybe it still finds some like things that match on one chunk versus another. But,
Yep.
Yeah.
Yep. So that's one reason. Maybe more concretely, when you search for model in repetitive loop, you get things like this. When you search for model in repetitive loop with your SAE, you get things like this. Why? Oh, sorry. Maybe let's leave aside the SAE thing for now, because I haven't actually explained the method. Why do you get stuff like this and not like this with semantic embedding vectors?
Is it because, like, with the SAE, because you have so many more examples, it's kind of when the thing is shown rather than described. So maybe like semantic embeddings count more like talking about repetition, whereas the actual maybe like active repeating is like a more subtle thing that comes over a large data set and get picked up by an SAE.
Something along the right lines. Any other guesses?
I feel like maybe this is similar to what you
said. Dennis, did you have a guess?
Yes, so maybe there are just repetition latents, something like that.
Yep. So yeah, I think why can the SAE do this is, I think, more obvious question. Yeah, maybe I'll take a final guess from Ritesh.
Yeah, I was thinking the same. Maybe there's a latent which tells the model it's repeating the output.
Yeah, so I mean, yes, models definitely will have a kind of, I'm in the middle of some repetitive text latents, because if nothing else, it makes predicting the next token really easy. You're in a repeated loop. You're doing loads of induction. You get so much loss. Life's amazing. It's model paradise. But yeah, so the problem is that the way standard embedding models work is they're kind of embedding things. So text with similar meaning is kind of high cosine sign. The problem is that model in repetitive loop is not actually semantically similar. to this text. This is text that contains a model in a repetitive loop. And I know there are certain kinds of retrieval models that kind of are specialized and have like a query embedding and a separate answer embedding. I can't remember if we used that baseline, but with SAEs, rather than trying to embed the word, rather than embedding the text, which would kind of have similar issues, in my opinion, you can just search over the autointerp labels and then just find the ones that are similar, or just like give it to an LLM and say which of these is most similar, and then just use that, and it just works. Or at least works in this context, which is probably cherry-picked for being unusually interesting. But that was cool. You can also do things like only cluster things using the latents to do with some concept or category, which is pretty hard to do with normal semantic embeddings, I think. An even cooler thing is that this unlocks things like dataset diffing and finding arbitrary correlations that are kind of pretty difficult to do with just normal embedding models. So for correlations, you can just say for all pair of features, how often do they co-occur in this dataset? How often do they co-occur in some control dataset? The things that have the biggest change and a large enough sample size are correlated. Or like, let's test this on a validation set or something. And I'm not confident there are that many use cases of this, but like I think it's pretty interesting to be able to just find arbitrary correlations, like this one of in chatbot arena that is often used by random degenerates. They often have narrative and roleplay stuff associated with the user asking for something offensive. So a model trained on this might pick up that kind of spurious correlation. I don't really care about this one, actually, but probably there are other ones you might care about. And I may be most excited about dataset diffing. So the idea here is you kind of look at which latents are present in a greater fraction of documents in dataset 1 than dataset 2. If so, that's probably a property of dataset 1. And I think this is kind of a big deal because diffing is, I think, just like a fairly generally useful thing to be able to do. Or like this is the one of the 4 that I most frequently recommend to people they actually try. You can also get LLMs to do diffing, but it's kind of different and more janky and more expensive often. And one angle on this that I think is really cool is, you know, I don't actually care that much about data science for data science's sake, but I do care a fair bit about understanding models. Models produce a lot of data. And if you can understand the data, that can give you insights about the model. Like here, we took model responses, the same set of prompts, and found that cautiousness-related latents were way more common in Grok 4 than any of the other models. And that this was like the biggest difference. Nothing to do with like racism or edginess or anything like that. It was just like a more cautious model that laid out its assumptions better and just, yeah, seemed more ambiguity aware. And yeah, all right. Zooming back out, though, I think there's like a really cool set of tools here and many projects to do with using these to understand models in interesting ways, I think could be pretty great. Though I'm not super excited about people just iterating on the tools themselves. Yeah, zooming back out, other examples I like of SAEs being good for unsupervised things. I'll talk about one of my favorites, auditing games, tomorrow. But I think the key takeaway I want people to have from this is SAEs are good for unsupervised discovery. If you know what you're looking for, use supervised methods, basically. And All right, so what are the most important other things? I think, yeah, it's maybe worth talking about kind of pathologies of SAEs and developing better metrics for SAEs and like roughly how that went. So in my opinion, I think that in hindsight, trying to break SAEs should have been a priority much earlier. But kind of towards the second half of 2024, a bunch of weird pathologies started to arise. One of my favorites is feature absorption, which, yeah, I will demonstrate via the clearly most efficient route of looking at the t-shirt I have explaining it. And yeah, so basically the way feature absorption works is sometimes you have two concepts, one of which is a strict subset of the other, like elephant and starts with E. What we want is have a feature for the blue circle and a feature for the red circle. But that is less sparse than the weird gerrymandered bullshit of take the blue circle, cut out the red circle. So that means starts with E, but is not the word elephant. And, you know, that activates less often. It's sparser. But, like, it's also clearly bullshit. And, yeah, models learn these things. Lovely paper from David Channon and Joseph Bloom and a few others. And linear probes for starts with E work totally fine. I think this was one of the first kind of cleanest examples of sparsity coming apart from interpretability. I think another one is this paper from Bard and Patrick, two of my 6.0 scholars, called SAEs Do Not Find Canonical Units of Analysis, which is basically an overly pretentious way of saying a thing that at least I thought might be true initially was that there was some ground truth that SAEs were tapping into, some like underlying set of concepts. And if you just made the SAE big enough, you would get these. I don't know, that seems not true. So specifically, we found kind of a few pathologies. The central one is that, let's see, we've probably got a good diagram somewhere. Maybe I should put this on the t-shirt. We have, suppose you have a model that represents colored shapes with kind of linear representations of colors and linear representations of shapes. You want the small SAE. You do not want the large SAE that is kind of taking the intersection of pairs of concepts, because that's kind of weird. It's not a natural concept. You're just combining things the model views as independent. But YOLO, it's sparser, so it happens. And I think that this is actually a pretty fundamental issue with sparsity as a proxy. You can think of, yeah, one way you can think of this is just like, as the model becomes bigger, sorry, as the SAE becomes bigger, it has more representational capacity, so it'll find more things. And we know that SAEs that aren't super big miss tons of stuff, like concepts that are just totally not present, which they also had some nice work on here. But as you make them bigger, you start to get these issues like absorption and composition and other things like feature splitting, which is debatably an issue, which is where like a high-level concept like animal breaks apart into like individual animal concepts, which you can kind of think of as what happens when you take feature absorption to its logical conclusion. Because like if you keep cutting out different animals such that you have animals apart from like dog, cat, wolf, pig, lamb, bear, etc., you just have this like weird rump feature left, and like maybe it just dies. Or like maybe it's just been fully decomposed into all of the important animals, or I don't know what. And an interesting twist in this saga was the Matryoshka SAEs paper, which was simultaneously discovered by a guy called Noah Nabashima and Bot, one of my scholars who worked on the previous paper, who was sufficiently offended by the failure modes that he wanted to fix them. And actually, this went surprisingly well. And I think these were a major improvement. And basically, what happened is they found that you could train an SAE that was kind of many nested SAEs, where you could either just randomly sample the first n latents and make everything else 0, or you could kind of have like the first 8, 16, 32, 64, etc. And you're kind of simultaneously training all of these prefixes, kind of randomly sampling for efficiency, to do well at reconstructing something. And this turns out to do way better on a bunch of issues like feature absorption. See this graph. Can anyone tell me why?
So it doesn't have the incentive to like split the feature.
Why not? Sparsity. We're still training it with sparsity.
Yeah, but you can like it can compose using that prefix, wouldn't it?
But I don't know, why couldn't you just have like a starts with E latent and an elephant latent? And just be like, yeah, this is fine. Oh, sorry, a starts with E except for the word elephant latent and an elephant latent. Why couldn't you have that?
In that case, you're like kind of paying a loss twice on elephant tokens.
Why?
Because I'm not sure. I'm sort of analogizing this to like you do like hierarchical linear regression, and you have like a loss term on pieces that like you have like group losses and then individual losses, and so like paying a penalty for like the model in that case like prefers to put stuff on the group because it's a smaller penalty than like spreading stuff out among the individual pieces or putting too much on both. It's like having a prior for the group, and it's cheaper to put weight there.
Yeah. I think it's broadly along the right lines. So the way I'd frame it in interp speak would be, suppose from the perspective of the SAE that is the first 30% of the model, say, it doesn't make sense to do feature absorption because it doesn't have capacity. From the perspective of the biggest one, it does. But from the perspective of the small one, it wants to have a starts with E concept, because that is, economically useful, or however you want to think about it. If it's got some limited budget to spend, that is worthy of its budget. Therefore, we can take this and say, and it will probably learn a starts with E concept early on, because it doesn't care that the later one would be slightly more efficient if that was missing elephant. This SAE does not want to miss elephant. And the later one only has like a mild preference, so like that doesn't dominate. And basically this is like a form of regularization that means the model wants to have high-level simple concepts rather than fragmented niche ones whether because they're just like small chunks taken out of a gerrymandered thing, or because they're the and of like a bunch of different concepts. And it might also learn an elephant latent later on, but it will, it'll just be like, all right, this is fine. I'm going to, it'll just be like, all right, actually, maybe getting the diagram back up. I think that if the elephant latent here is kind of representing the starts with E information and the I'm an elephant information, this can just represent the I'm an elephant information because starts with E is already there. And yeah, I don't know. I like Matryoshka SAEs. I basically think everyone should just train Matryoshka SAEs. I don't think they like fully solve the problem with SAEs, but they are kind of a note of optimism in that I think they made significant progress. And one thing that I think is especially worth highlighting is that they are actually worse according to the standard metric of like how much of the model is recovered. But they are much better on these other metrics that we think also matter. And if you are a naive man of a single metric, you would be like, fuck this, why would I use that? But you would be wrong. And the kind of fundamental problem is we don't really know exactly what we're measuring. I mean, I don't even know how to aggregate these. Like, what is an acceptable amount of loss in the variance for like this amount of improvement in feature absorption? Does feature absorption really matter? This is all kind of unclear. And one of the big reasons I'm like very excited about downstream tasks, I feel like they are the least terrible resolution to this problem. Take objective things that are difficult and benefit from being good at interp. Try doing things, see what happens. And yeah, I don't know. For the curious, one of my other Mat 6.0 papers was SAE bench, trying to make like an SAE benchmark under the premise of like, we don't know the right metrics, but we can come up with a bunch of things that we care about, like, does absorption happen? Can you get concepts? Are you interpretable? Do you recover the right loss? Do you disentangle things we think ought to be disentangled? E.g., can we surgically remove a model's knowledge by messing with biology-related latents without messing with other things? Things like that. And yep, and no, I did a lot of SE projects. I think maybe trying to return to like, well, what are the takeaways here? What you're measuring really, really matters. Yeah, let me see. Maybe, yeah, so what you're measuring really, really matters. If you just have a simple metric, it's easy to kind of mislead yourself. If downstream tasks are epic, and I have other takeaways. Sparsity is a bullshit proxy that caused loads of issues, but it also was surprisingly addressable with some fairly incremental tweaks to how we made SAEs. What this means is kind of confusing and left as an exercise for the reader. Great, very concise takeaway. Doing this via dictation is much more efficient than typing it. Oh yeah, sidebar. If people are doing things, especially things that involve a bunch of talking to LLMs, including vibe coding, highly recommend doing it via dictation. LLMs can just understand your dictation with very little effort. I personally find it faster and more free-flowing. And yeah, I think it's often easier to get thoughts out. All right. So maybe the final place is just like, where are sparse autoencoders at today? So, or maybe I'll call this dictionary learning, because I think one of the developments is that people, do stuff that is not SAEs. So I think that by and large, yeah, I mean, there's like, the field has like somewhat splintered, I think for the better, into different directions. So e.g. there's like cross-coders for model diffing, SAEs as a tool for model biology, stochastic parameter decomposition as a, I don't actually know exactly how Lee would describe this. I'm just going to go with like tool for circuit decomposition, where, and kind of, let's go with transcoder-based attribution graphs. And I think my opinion on these two, cross-coders, the key idea for those who are not aware is if you want to compare two things, e.g. a model before and after fine-tuning, you can take the concatenation of the residual stream in both on the same input and train a sparse autoencoder on this concatenated residual stream. If there are shared concepts, then they should kind of have then they'll kind of use a shared latent. If there are different concepts, there's got to be a latent that does something in one and not the other. And they're like a reasonably useful tool. They're not super hard to train. They kind of work. There are various alternatives. If you want to take on model diffing, Tag, Julian, or Clement, two of my 7.0 scholars who did a bunch of cool work here, including fixing some bugs and crosscoders that made the technique work much better. I'm, a pretty big fan of like SAEs as a tool in a researcher's toolkit, but remember, they are not the only tool for doing unsupervised discovery. There's a ton more. Like, I think that sometimes people do what I consider the mistake of being kind of overly blinded by SAEs as like the one possible method for just unsupervised discovery, when I think it is correct to think of SAEs as like one of several that has various advantages. Sometimes it's the right thing to use. Sometimes it's a fucking pain in the ass. Things like cross-layer transcoders are vastly more a pain in the ass. And we've largely decided it is not worth the effort of training internally. But yeah, I think that maybe off the top of my head, other example unsupervised discovery methods, just talk to the model. Many kinds of model diffing techniques, including black box ones like KL divergence per token, which is when you have a model vector and you ask it questions about a mysterious token, and you replace that token's embedding with your vector, and this often magically works and tells you things about what's stored in that vector. I would consider thought anchors to be something that can tell you things about the model's reasoning. Reading the chain of thoughts, I think, can be extremely useful as a method of unsupervised discovery. Just trying a bunch of prompts, possibly by a language model agent doing this, I think is another valid and useful method. Come up with random concepts and probe for them. Extract steering vectors, steer with them, see what happens. There's probably a bunch of other niche ones, but I think that basically covers the ones I can recall recommending to people. All right, these bullet points are getting more and more chaotic. I'll share these notes afterwards if people are curious. Hassan?
Yeah, it's just a quick question on, like, reading the chain of thought is like a very sort of manual and like it doesn't scale well with like directly you reading chain of thought. How have you found like LLMs reading a bunch of chains of thoughts and like aggregating what their hypotheses are, like as an unsupervised method?
So this is a good question. There is kind of an emerging field within a kind of AI control called chain of thought monitoring that is kind of attacking this question from the angle of, if you kind of want to look for specific things in the chain of thought, how reliably, if you want to detect bad behavior in the model, how reliably can you do this by looking for specific things in chain of thought, which is like somewhat related. There was a great OpenAI paper from Bowen Baker on this. For the like more interpretability related question, we've like, I'm not confident there's been any great work on this. Anthropic had this excellent automated auditing post. Let me see. Does that talk about chain of thought? Nope. Sad. Yeah, my like rough experience is it's okay. Like basically models aren't amazing at nuance. I think that models can, like if you tell the model, find me interesting things, I expect this to work much less well than like, e.g., here is what I expect to see. Tell me things that do not fit this, or find me things that have the following property. For example, if you want to find an evaluation-aware model, I think that's basically something an LLM could do completely fine. And there has, in fact, been a bunch of good work on this. I think the most notable from Nicholas Godowski-Dill at Apollo, that found things in Claude 3.7 Sonnet chain of thought, like this is an alignment evaluation that tests blah, blah, blah correctly. And LLMs seem to work pretty well for this. I think they get lots of false positives. They're not very good at telling the difference between, the model is talking about testing as a concept, but not necessarily talking about being tested itself as in it is in an evaluation and things like this. But like this is kind of fine because you can just manually review them or like get a more stringent and focused LLM filter. I also think that generally the more you're willing to spend and the longer you're willing to wait, the better, because big LLMs that do lots of reasoning, like, I don't know, I would guess that probably Gemini 2.5 Pro with a big thinking budget, GPT-5 High, or 4.5 Sonnet extended thinking would all do pretty well at nuance. But it's kind of still like a nascent field, which is like the broader question of like using models to understand models, even in this like fairly black box sense, I think is like pretty interesting. I mean, a theme I'll probably talk a bunch about tomorrow is I've been pretty surprised by just how interesting black box methods can get, especially kind of as reasoning models have become the standard. And, things like, what's the best way to read the chain of thought? Are like really instructive and can tell you really useful things. And basically just an LLM wrapper wrangling task that is not conceptually very difficult, but you kind of often does benefit from a scientific attitude that, an interpretability researcher is probably better than average at having, of like, is this actually getting what I want? How would I know? How would I know if I'm missing things? What exactly is the thing we care about? What can I build a scaffold that would do this better, etc. But I don't know. You can assume that anytime I say read the thing, have an LLM read the thing is also within scope. Using the data-centric interpretability methods is also within scope. So like, that's a valid thing you can do. You could take the chains of thought on some set of prompts. You could edit those prompts to make them benign, and then you could look at which latents are like particularly different between the two, or even just which latents are like common compared to how common they are on just like general internet text or something. I'm sure that would get you lots of false positives, but I think that when we're talking about unsupervised discovery, it doesn't actually matter that much if you get lots of false positives, because if you kind of what matters is that if there is a good hypothesis, you found it somewhere in your top like 100, so long as testing hypotheses isn't that expensive. And often the test can just be, you just literally read them and you say, is this obviously stupid or not? And you can read 100 things and say if they're obviously stupid, and it's a bit tedious, but it doesn't take that long. And yeah, maybe you discover, maybe 2 of them were like really important hypotheses. I think this is important, particularly important to stress, because I think that people often conflate the I want to perfectly reverse engineer the thing, or like I want to be really confident I've missed nothing, where things like precision are pretty important, with I want to discover true hypotheses, where it's kind of fine if you miss some things, and it's also fine if you have like loads of random garbage in there that's false. You just need to find the true things. And I think that, at least personally, I find it quite easy to slip into a bit of a perfectionist mindset in interpretability of like, this must be perfect, this must like accurately get everything. And if half of what's giving me garbage, I don't trust the method. And I think this is not actually the right instinct in many cases. And I have tried to break it in myself with moderate success. Yeah, no. People who come from like a pure mathsy background or theoretical physics or stuff like that are maybe also more likely to share this inclination. But yeah. All right, so unsupervised discovery is important, but there's other things. Maybe the final one I'll talk about is kind of transcoder-based attribution graphs. So, you know, I'm sure most of you have seen, but for those not aware, Anthropic had this very flashy pair of papers on making cross-layer transcoders, basically a fancy version of an SAE, but with the key difference that rather than just approximating a vector, they were replacing chunks of the model, notably MLP layers, with a sparse replacement. And then now they had a vastly simpler model. They also made some other YOLO assumptions, like attention is constant, and were able to use this to understand like what's happening. Or like, well, you know, the claim of the paper is that they are able to use this to gain insight into what's happening. And they have like a bunch of fancy algorithms for analyzing this kind of graph of concepts, where kind of each node is the things in the cross-layer transcoder on that token that are important. The cross-layer versus single-layer bit isn't actually very important, in my opinion. It's more like an implementation detail that improves efficiency but doesn't change the qualitative results. And yeah, transcode is like very similar to an SAE, in my opinion, at least conceptually. Though they do let you do things like have a simplified model because you took the chunks that were complicated and replaced it with a thing that was simple. But, you know, things like, they're made up of units. The units are often interpretable. You can interpret them with max activating dataset examples, things like that. All basically just works. And in my opinion, I think this is great model biology work. I think this is terrible reverse engineering work. Because I think that this just has a ridiculous amount of error when you're trying to think about the actual underlying thing in the model. Because you're replacing it with a replacement model. This has a bunch of error, and the error compounds. Like, you couldn't really run this replacement model. It would just completely break. Moreover, you can, we don't necessarily understand what all the things mean, and we might have misinterpreted some concepts, and we need to do a bunch of pruning on our graph to get it down to the important bits. And I like broadly buy that this is a reasonable method for finding the broad strokes of some phenomena. The thing I was showing you was like the kind of methods half. This is the like case studies half. My favorite is this discovery of implicit planning in models. I guess Dennis here has been doing some really nice follow-up work on, where they found concepts for like the line should end in rabbit, and found that this lit up like here or something, and that they could change this to something else, and the model would then generate the next line in order to make that happen. And I'm like, that's fucking cool. I had not seen this. I wasn't massively surprised, but like I had not thought to check this, and I think it was the first good example of like mechanistic evidence of models choosing the tokens they generate in order to enable themselves to generate specific things down the line, rather than myopically choosing the next token. Or like, it is myopically choosing the next token because that is the most reasonable next token if you're predicting what a human poet would have written, but it's like mechanistically not myopic. And this is like, yeah, this was great. But then they also had, say, yeah, I don't know. Kind of things varied quite a lot. Like they had this really nice one trying to understand a jailbreak, where you kind of give the model some words whose acronym is bomb, harmful thing, and then the model often gets jailbroken, and they were like, why? And they found some things like, oh, the certain concepts that would have been relevant for refusal like didn't activate at the right times, and then it was a bit too late, and the model kind of got in flow, and when it's in the middle of a sentence, it doesn't want to refuse, but if you put in a full stop, it will, because models have like a very strong prior that sentences don't magically end in the middle. And yep, I don't know. These are great, but I kind of don't really see a coherent path from any of these to anything I would remotely consider kind of fully understanding the thing, or being confident you're not missing anything, or like a really precise understanding that I believe is mechanistically faithful. I think it's just stacking a lot of approximations on top of approximations. And I'm a little bit confused by what people who are excited about the reverse engineering agenda are like exactly hoping for here. I think that like as a tool for model biology, it's like, it seems like a pretty good one. I'm like fairly persuaded. I think I'm most persuaded that attribution graphs are a reasonable thing to do. That is, find some way, however you want, to decompose the model into concepts, and then do some kind of pruning algorithm to figure out which are important and how they connect up, and study this. I am not immediately convinced there are like important things we can learn by looking at the circuits that we couldn't have just gotten from like 1 to 3 SAEs at different points in the model. But I'm sure it exists. It seems plausible. And yeah, I think that broadly, broadly, I think it's a useful tool. We've also found internally that cross-layer transcoders specifically are like an enormous pain, and much more of a pain on, especially on big models, than like normal SAEs, because normal SAEs are kind of like a small-ish thing, and you just train a bunch of them for different layers. Ditto single-layer transcoders. Cross-layer transcoders are more like you kind of glue lots of transcoders together into one massive thing you have to train simultaneously. And it has a ridiculous number of parameters, and quite a bit more parameters than you'd get by just kind of concatenating all the transcoders together. It's annoying. And there are various efficiency hacks you can do, but ultimately just needing to have many, many parameters is extremely annoying. But you know, maybe Anthropic will convince me that they just keep discovering really epic stuff with this, and they can't see how to do it with other methods. Though I think a fun exercise is go through this paper and for each section say, all right, I have a model. I do not have a cross-layer transcoder. Maybe I have like 1 SAE or 2 SAEs. How could I have replicated this case study? I think probably for some of them, I don't really know what I would have done, but e.g., this was kind of the seed of Dennis's work, showing that you could find steering vectors for rhyme with it or something. And that's easy, and you can do it on many models. You don't need to train anything, and I think it basically shows you what this shows you. And I think that, yeah, kind of like, what is the simplest and stupidest way I could achieve some result is like a really good exercise and a question you should always ask yourself when doing research, because at least some fraction of interpretability researchers, myself included, have a bias towards like things that feel pretty and elegant, and sometimes this means really complicated and messy and not really thinking about pragmatic reality. You know, like, maybe I'm like, how can I design an amazing autorater that can perfectly figure out which chains of thought I should look at? When in fact, I just have like 30 chains of thought and I could read them all in 2 hours and I should just do this. And this would suffice. Or maybe I have 500 and that's a bad idea and I should do the methods. But like, it should always be grounded in thinking like that. Though I think one kind of interesting thing is cross-layer transcoders are kind of like a massive one-off infrastructure investment, where the kind of vibe I get is once you have them, you can make tooling such that researchers can use them very easily. And I mean, you can play around with NeuronPedia's circuit tracer tool, or watch a video that I did with Jack and Emmanuel from Anthropic, who were kind of leads on this work, where they kind of walked me through how to play around with attribution graphs on NeuronPedia's tool. And like, I think this is like a pretty interesting exercise. But if you have a model where you haven't done this, then you kind of never want to do this for a specific investigation. But if you had done this, maybe the costs distributed across all of the projects, especially if it's a very widely studied model, or like a really large team, or like a popular open source one, maybe that's enough to make it worth it. And I don't really know how to reason about trade-offs like that. But yeah, my final highlight will be, I think they had this really fun addition case study, basically looking into as many different mechanisms as they could of how addition worked. And it's fucking cursed. I think there's probably worse ones, but you know, each of these is kind of like, this is kind of a flowchart. There's like a bunch of different mechanisms. There's some kind of rough heuristics, like, we can kind of round them to a thing. There's some like a bit finer heuristics, and then there's things that are like mod 10. And do they have other stuff? Whatever this shit is. And yeah, I find this interesting because I'm pretty persuaded by the argument that I don't know how I would have done this without a tool like attribution graphs that is unsupervised and fine-grained and kind of computation-focused. But on the other hand, I don't know if I think that it is a priority to be able to get this level of detail, especially when I think you could get things to the level of like, well, there's a mod 10 circuit and there's a kind of round circuit without anywhere near this level of pain. And maybe that's all you need. Maybe those qualitative statements are sufficient. Maybe they're not. I find this kind of hard to judge. It'd be great if someone made a downstream task that was both a convincing task and also relied on having a really fine-grained understanding like this, which is the main way I could imagine updating significantly here, where I'm happy with like kind of ad hoc downstream tasks, like someone demonstrates, we discovered X about a model, and it really couldn't have happened if we hadn't had these tools. And I'm like, okay, X is great. I think this was a good investigation. Maybe we can simplify this, and we totally should, because I don't want to use complicated methods, but like this is a good validation of the complicated method. But anyway, that is probably all I want to say on transcoder-based attribution graphs. So maybe trying to summarize that. A pretty good tool for model biology. A tool where I don't see a clear path for how this would lead to ambitious reverse engineering. I think I'd probably use them if I had them easily available, but they're an enormous pain to do well, especially the highest quality cross-layer transcoder versions. And I think that often simpler methods seem like they would suffice. It seems like there's a certain depth of understanding that would be hard to gain otherwise, but it's kind of unclear to me if this matters. And yeah, L?
Oh, I was a little bit confused because when you were looking at the page that was describing the methodology and you were saying like this is replacing the MLP layers of some sparse version, I think you said something along the lines of like, this kind of like breaks the model behavior and it's like no longer really the same model. But like also in the biology examples, it seems like that's a model doing reasonable things. So I'm trying to understand.
So they're cheating, basically. So what's happening is when you introduce an approximation at every layer and you run the model, the approximations accumulate and blow up and your model dies, basically. I think that is also true of cross-layer transcoders. It's definitely true of SAEs. I can't remember the details here. Let me see, do they have lost recovered? Nope. All right. But yeah, I think that, if you tried to run the model with the cross-layer transcoder instead of the MLP layers, it would do pretty badly, it's my guess. Though, one uncertainty there is that the kind of cross-layer aspect means that there might be a bunch of stuff that kind of is known by the first layer, like you kind of know what concepts you need, e.g. the token is the or something. And then that has a predictable component in the output of every layer, but it was computed with like only one step, so there was no room for approximation error to accumulate. But like I predict it's going to do pretty badly. What they do when they compute these attribution graphs is they kind of freeze each cross-layer. The way to think about it is it's a local exploration on the model's behavior on a single prompt. You have a specific prompt. You run the cross-layer transcoder on the model's activations there. You observe what activates and what doesn't, and then you freeze that. You can kind of think of this as like every ReLU is a binary mask and then a linear function, either 0 or the identity. Or maybe every ReLU is an identity and a binary mask. You freeze the binary mask, so now it's the identity and applying a mask. And now I think they might even not even look at how things go through one of these nodes. They only look at like, well, what's the input to this MLP layer? Well, it's the sum of the output of all of the previous layers, and we can break those down into kind of like transcoder latents. So now we can see how each of those connects to each of these because it's basically a linear function. But you don't kind of propagate that through. you just treat those as edges in your graph, because you kind of want to distinguish between A makes B light up and B makes C light up from A makes C light up. And one other important detail that I forgot to mention is this idea of error nodes. So the idea of error nodes is basically yeah, they have a fun, long annotation section, which I liked. So yeah, basically the way to think about error nodes is to say, I think that I've probably missed a bunch of stuff in my SAE. So I want to add a node called question mark, question mark, question mark to represent all of the stuff I didn't explain. I don't know what this stuff is, but I can kind of say it's exactly what would be needed to make my approximation perfect. In other words, the difference between the true thing and the reconstructed thing, the error, thus error nodes. And basically, you can just treat these as a node in your graph. They are much more complicated as a node than like the things next to them. But this is kind of fine because we're freezing the nodes. We're not looking at the internal computational structure of a transcoder latent. We're just saying, whatever, we're going to freeze it. And we're going to look at the like things that contribute to it. I think they might not look at things that contribute to error nodes. I can't remember. No, maybe they do. I don't know. Diamonds are error nodes, circles are transcoder latents. And so yeah, another way you can think about not breaking the model is you just have error nodes, in which case there is literally no approximation error by definition. This is useful because it means that you can say things like, well, I'm pretty sure this part of the input means, national, this part means group, etc. But then, there's everything else on layer 12. That's an important input feature, apparently, kind of earlier on. Why is this important? Nobody knows. And you might make guesses. It might just be that it's some kind of bias the model's depending on, though I hope they have bias terms to address this or something, because that's like a pretty easy, low-hanging fruit. And yeah, so basically, in my opinion, if you want to claim that you have like reverse engineered or understood your thing, you are not allowed to use error nodes. If you're doing model biology, you are allowed to use error nodes. And if you remove all the error nodes, you normally just do terribly. Yeah, this is a thing to watch out for if you do look at dictionary learning papers and that do circuit analysis, because you kind of often need to include the error nodes, otherwise it all blows up. But now you're not really testing the right thing anymore. And so you kind of want to make sure you also get their metrics without error nodes, which are often much worse. So like sparse feature circuits, which is one of the first kind of finding circuits with SAEs. This didn't do transcoders, rather it used kind of gradient-based approximations to activation patching called attribution patching that you can read about in Nanda et al. Basically, they have various interesting graphs where they, so like here, I can't remember what faithfulness and completeness mean, but one of them is like, how bad is it to get rid of your stuff? And the other is, how bad is it to get rid of everything else? Oh yeah, I think completeness is if you delete everything you think is important, what happens? Faithfulness is if you delete your thing, what happens? And, The blue line up here is the feature circuit. The red line down here is the feature circuit without SAE errors. Reading the y-axis is left as an exercise to the reader. And residual stream errors, I think, are particularly bad. In this paper, they had SAEs on the residual stream, SAEs and MLPs. And residual stream errors are like particularly bad because kind of everything has to go through the residual stream, while often computational paths only go through like a few of the layers. So, you know, maybe the green line is fairer. I would have been happy with the paper if they didn't have residual SAEs at all. And this is like not terrible, but it's not great. And note that this is in the, you kind of are allowed many, many SAE latents. And then with Janoscope, they're closer for some reason. I like to think it's because we have better SAEs, but who knows? Maybe Gemma is just that nicer, or it's something to do with having more layers, or who knows. But yeah, I think maybe I'll try to roughly wrap there, and we can leave these for tomorrow. I will get through this eventually, I promise. But yeah, I think there are some SAEs are a useful tool. They are not the magic bullet that solves everything. Many people, including me, were too excited about them, in my opinion, but they totally have uses, especially for unsupervised discovery and like for a handful of other things. But if you can use a supervised method, you probably should. And generally, just like always ask yourself, always ask yourself what the simple baselines that might just work are, and make sure you check those before you sink loads of time into a difficult, expensive, fancy method. That would save a lot of research projects a lot of time. And especially if it's kind of a project where the goal is not to make a fancy technique, the goal is to do something. I think that like we didn't really have good metrics, and this held back research a bunch. I think strategically, it would have been good if we'd invested more in having metrics, and I have become way more excited about downstream tasks as a result of this whole saga. Though I kind of think on conceptual grounds, they kind of make sense anyway. Credit to people like Stephen Casper and Buck Schlegeris, who've been arguing with me for a while that mech-interp people should use downstream tasks more. Base points to them. And yeah, I think that there were also some kind of conceptual issues with SAEs that we kind of found out, in my opinion, later than we should have. But they kind of seem surprisingly addressable, and like there are totally remaining issues, but maybe those are also addressable, kind of unclear. But in my opinion, I don't really see a realistic path to getting error so low. I see this as a tool for complete reverse engineering. Though probably proponents of that might argue that I'm like strawmanning them and I'm holding them to too high a standard, and you can achieve like ambitious reverse engineering without getting close to complete reverse engineering. Semantics. I think what do I think? Yeah. Oh yeah, maybe another meta takeaway for me, that's less actionable for you guys, is releasing open source SAEs was a great idea, and I think spurred a bunch of research that was very helpful to me in updating against the whole thing, but also in illustrating what SAEs were good for. And I think that doing public goods like this, that's like a bit too much of a pain for most smaller actors to do, can be really fruitful. And this also covers things like making open source tooling that you really do not need a Frontier Labs resources to do. I mean, you also didn't need Frontier Labs resources to do Janoscope. Some academic lab in China did a pretty good representation on LlamaScope. I don't know. I do think, especially for people generally trying to get into a field and trying to like demonstrate that they can do things and like get to know people and make a name for themselves, I think making good open source contributions is a pretty good strategy that I think is often underrated, though they kind of need to be good open source contributions. But e.g. Clement made an interp, which seems pretty epic to me, which is basically taking an Insight, a very high effort, bunch of people working on it, legit library, taking a feature in transformer lens of you can run the same code on many models, and just writing a bunch of tedious wrappers that meant you can basically treat an Insight like this, that I really don't think was that difficult, but I think is just actually very helpful. And I think often, I don't know, if you're like post-exploration phase trying to figure out what to do with yourselves, you will probably have reasonable intuitions for what kind of research tooling you personally would like. And I think this probably correlates somewhat with like what the community would like. And I think that for people who kind of can do software engineering, but like haven't done research, not knowing what researchers need is often like quite a big bottleneck. So, end sales pitch. And, you know, where's actually learning out today? People are doing a bunch of things. I think there are useful tools here for model biology. I would quite like to do things like train 1 or 2 SAEs on like the biggest Geminis and see if they're useful for trying to audit them and things like this. And I think that doing this is like annoying, but very doable without that much time. I think things get much worse when you're trying to do SAEs everywhere rather than just a single SAE. Or if you're trying to make the SAE like super wide, which I think is nice but not necessary. And yeah, but like there's a bunch of other things. And I think that SAE, Transcoder, or whatever based circuit analysis is cool. I think it is like probably useful to the degree there are like good open source tools for this. I mean, yeah, Neuronpedia both has some things you can play around with. Yeah, Neuronpedia both has some things like this. And let's see. Yeah, okay. What model does this allow? Yeah, it also supports Qwen3 4B, which is pretty cool. Some of the Anthropic fellows, Michael Hanna and Matej Petrovsky, did this. That's great. We also had just randomly decided to include transcoders in Gemascope. Credits to Arthur for just unilaterally deciding to do this. And then no one used them for like 6 months, and then cross-layer transcoders became cool, and you could also use single-layer transcoders to do this. And this meant that there was now just like open source things. That was great. Which has updated me towards just do random shit, which might be useful someday, who knows. But yeah, I recommend playing around with this. I think it's educational. And I particularly am excited about the like Qwen3 4B ones because you can put kind of thinking, like I think you can generate your own by kind of like putting in some prompts and then getting a graph, and Qwen's a reasoning model, so you can do kind of more interesting things here. Though I also predict that the UI is going to be a headache for reasoning-y traces. There's also the problem that on reasoning models, attribution graphs work much less well because if sentence 1 made sentence 2 happen and sentence 2 made sentence 3 happen, you don't see the sentence 1, sentence 2 link because your loss is what made sentence 3 happen, and you're only looking at kind of differentiable connections. And so something that goes through making the model say something just doesn't show up. But I still think you can probably get a bunch of cool insights from this, and this is totally a good source of mini projects. Yeah, if you have issues, you can ping Johnny, who runs Neuronpedia, on Slack.
So could you explain the issue with reasoning models again? I think I didn't understand.
So basically, if, say the reasoning model is planning an essay, and it writes the title, and then it writes the kind of subheading because of the title, and then it writes the first sentence because of the subheading, but not because of the title, because the title was kind of superseded by the subheading. If you do an attribution graph on, say, a certain token in the sentence, you're studying the function that maps all of the text up to the token just before that to that special token. And this is kind of conditioning on all previous sampled tokens just being kind of God-given. It doesn't know where they came from. The fact that the logit on, you know, Apple, it made the Apple token happen here is not featured in the attribution graph, because it just isn't. That isn't like how they're set up. And I don't see a obvious way you could convert them to work with that. That there are like some dumb hacks you could try, but it would be a clusterfuck. And yeah. Another way to think about it is late layer activations are cause early layer activations on subsequent tokens. This fundamentally breaks the assumption you've done in most of MechInterp, including attribution graphs, that causal flow goes like this. But anyway, I'll talk a lot more about reasoning models tomorrow. Possibly I should just do a separate thing on reasoning models. Who knows? Maybe I'll begin with reasoning models and then see if that will just clearly become the whole session or not, and see what happens. But yeah. All right. I am probably going to wrap up there. Happy to take questions if people have any of them and are still conscious after like 3 hours.
I guess one quick one is like if people like released some version of the circuit tracing transducer stuff and cross-coder stuff where like they had very low error and they got rid of the error nodes, like would that cause you to update about them being useful? Or like,
I don't think this is possible. So, or sorry, is what you're saying they can delete the error nodes and performance is still, yeah, like what is the performance if they remove the error nodes?
Yeah, and like, and they make the performance good. They make number go down somehow. And
how far?
I don't know. Yeah.
I'd feel like, all right, show to me that you can do something with these.
Like maybe they showed that like on downstream, like benchmarks, it still is smart.
So that wouldn't. I see breaking the model as a symptom, not the actual problem. It's more just like you're missing things. And this means you are not going to have complete explanations. Or at least you can't be confident you're not going to have complete explanations. And it also depends on like what kind of explanation you want. Like you can have a qualitative explanation. And I could maybe imagine being convinced that, yeah, like it's pretty unlikely there are additional important qualitative factors that are not included in that. But I would consider this model biology, not reverse engineering. I feel like for reverse engineering, you must be making much more quantitative statements. And I mean, another problem I didn't even get into is like, there's a sense in which it's not really an explanation if your human understanding explanation could explain many different internal like things, because the exact values of the activations and the exact values of the connections between them are not specified, but can matter quite a bit. Like, is it 20 or 80? Pretty big difference, but by the standards of SAE investigations, you said it would light up, and it lit up. What more do you want from me? So Yeah, I think that like I conceptually don't see a way that this method could not have error nodes. I would be surprised, but not enormously surprised, if they were able to remove error nodes and, you know, have 4.5 Sonnet perform at least as well as 4 Sonnet did, say. Like, that would be impressive to me, but it wouldn't change my mind on the, do I think you could achieve something qualitatively better than, like, these are the important factors, maybe we're missing some things, we don't think the things we're missing are that important.
Yeah. Kind of a random follow-up question. Has it been investigated to what extent error terms or error nodes are due to overfitting to training data on which SAEs or any other kind of DL was trained?
I'm not aware of anyone looking precisely into that. I would be surprised, like, SAEs, I don't believe, SAEs definitely don't do perfectly on their training data. I mean, often SAEs are trained in an online way. Oh, sorry. SAEs are trained like in one epoch. They never see repeated data unless your text data set had duplication. But yeah, I think that, what do I think? I think that, I mean, probably they are better on training data. Even if you're doing single epoch, you can still kind of overfit. You'll just never notice that you've overfit because you never evaluate on the things you've trained on. But I think that, let's see. Yeah, I think that by and large, I kind of just don't really feel like I need an explanation for error nodes. It's just, well, obviously, you're training an approximation. It's an approximation. It's going to have error. And oh yeah, one bit of data is in the SAEs do not find canonical units paper. They kind of showed that there did genuinely seem to be concepts that were kind of in the error nodes of small SAEs, but captured by large SAEs. So like, it's not just pathology. It's also capacity issue, though, you know, you can always be like, sufficiently large SAEs have never been tried. So yeah, and yeah, maybe to answer your question from the chat from ages ago about end-to-end SAEs. So for people not aware, end-to-end SAEs were this idea, I think from Lee Sharkey's group, that what if rather than training the SAE to approximate the activations, we trained it to make the logits as close to the original as possible? And it's a bit hard to evaluate because at the time they were still using metrics like lost recovered. And in my opinion, tail divergence of logits and lost recovered are much closer together than like mean squared error on activations, which means that if you're optimizing for KL, I trust lost recovered less, though I got into arguments with some of the authors about this. I think people have probably run them on SAE Bench, but I can't remember the results. I predict they are somewhat better. Yeah, Adam Carvonen, who kind of co-led SAE Bench, had like a fun follow-on project showing that basically showing that like if you train a normal SAE and then fine-tune on end-to-end, this works as well, possibly better, as just training from scratch. Which would kind of support some hypothesis that it's not really massively changing things. It's just like kind of rearranging them a bit and like getting rid of some of the like useless BS. And this, yeah, this was cool. I think there is like a credible argument that people training SAEs who care about quality should just do this. I'm sure Adam tested them on SAE Bench, given that he made SAE Bench, but I can't remember what happened. But I'm sure some of you could look it up afterwards and share it in random. Anyway, I think that, what do I think? I think that, yeah, kind of normal SAE Bench is just like, sorry, normal end-to-end SAEs are just kind of not worth the effort, I'd say. I think that they're just like quite a bit more of a headache to train, because the way people, at least people who care about like larger models or like doing things at scale, train SAEs is they typically save tons of activations to disk by running the model, and they throw the model away, and they just train a thing on those vectors to reconstruct those vectors, which is just much easier. And basically, yeah, it's, I think that words. I think that if you were doing end-to-end training, you kind of couldn't do this. You'd need to be running the model, or at least, at the very least, the second half of the model, so you could measure the loss. And I think that from a kind of how many resources you're spending on training perspective, you're probably better off just training an SE on more data. And it wouldn't surprise me if that just wins. But I don't know if anyone studied that specifically. But yeah, Adam's finding is great. Any final questions?
I guess I have one more, which is about the
sure.
Hypotheses paper. And I guess I'm curious there of like, my initial reaction is to be a little bit skeptical of like this being like maybe overly complicated way to get features out. And I guess I'm curious like what the baselines were about like, what if we just take concepts, right, and like run it through the LLM API, just a big list of concepts, or how much they actually save on like reducing the search space by using SAEs first, or like if that makes them miss important concepts that aren't represented in SAEs or stuff like that.
That's a great question. I vaguely recall thinking that the baselines were reasonable, but don't really remember much detail. If you want, you can have the challenge of going and actually looking at the paper yourself and deciding if you think the baselines are legit, and DMing me or posting in random with what you conclude. Might be a fun exercise. But I could not easily think of a clearly better method than what they did. Which is as good, at least. It's the minimal bar you need to pass. Though I endorse the instinct. Though I guess I will say, I think that the like SAE-based methods are kind of a, if you don't have to train your own SAEs, aren't really that bad. As kind of, I mean, you know, asking an LLM API is easier because LLM API is really easy, but I think that it's just not very difficult to say, what I think, it's not very difficult to like, yeah, just run an SAE. I mean, in the Dataset, I mean, yeah, the Hypotheses paper, they kind of trained their own SAE, but it was on embedding vectors. They didn't actually use that much data. I think this is probably fine. And not that much effort. I believe they kind of compare the costs. I hope they include the cost of training the SAEs, but I don't remember if they did. That would be a reasonable thing to complain about. And I think that, yeah. It would also be embarrassing if they turn out to be bad, because I had a prediction market on who will first beat baselines with SAEs that I resolved positively with them as one of the 2 positive contenders. And the other one is also controversial, but I stand by that decision. Anyway, all right, should we call it a day there? Cool, all right, see people tomorrow for what's new and exciting in Interp and what currently matters.